Hi guys, now we're back back on the Admiral and some more stuff about theory. Today I thought we would talk, after I show you what I've gotten done on here, talk about the picture tube. And I want to make a disclaimer for sure before anyone even so much as says anything in the comments. We're basically going to be all the circuit theory and everything and comparing to radios and all this stuff. We'll be dealing strictly with black and white TV. For one thing, it's what I got on the bench. I don't have a color TV. I figure if there's enough interest wanting to know theory and circuits on a color TV, then later, maybe this summer, I can work up a some videos on color TV. But for right now, this is all going to be about black and white TV. We'll be looking constantly, a lot of times, at the schematic of this particular TV, this Admiral, and of course comparing that to radios and stuff. Now today we're going to be talking about picture tubes, which there is no comparison to radio, obviously. So anyway, to get going here before I get too winded, and well, I seem to manage to lose my pointer, so we'll use this. Anyway, I started up in this little area here and started replacing the capacitors and any ion tolerance resistors. There were quite a few resistors that were out of tolerance. Basically, I think I believe this is the only one that I kept in so far that was actually in tolerance. It's a cathode resistor on the audio output tube. I've got the rebuilt cans, filter cans, all wired in, and I just continued on with part replacement and getting things hooked up and checking stuff. The next area now is I've got what I needed to do on this horizontal oscillator coil. Replace the cap, and the two resistors that was on it were out of tolerance. We'll start working in this area here, and I'll come down in here to finish up this point, and then we'll move up to the front and finish up here. So that's where we're at. Waiting on a resistor. I got it on order for this one here. I didn't have it. It's a 390 ohm 2 watt, and I didn't have any. There's also a resistor right up in here. You can't really see. Don't remember its value, but it's out of tolerance. So I got one of those on order too. So now the first thing I wanted to show you, and I'm going to talk about on picture tubes, I want to show you the picture tube out of this, because it's a non-aluminized picture tube, which means that it does have a magnet that goes on the neck, ion trap magnet that straightens out the electrons from the bent gun. But this picture tube's got a really nice bent gun in it that you can see real well, so I'm going to hope I can focus in that on that really good. Let me zoom in. So if you look at the gun, you compare it to the sides of the glass here and here, you can see it's got a definite angle to it. And there's a little bit telltale signs where the magnet's set. It's set right in here. So, and what the magnet does, basically, the magnetic field affects only electrons. It won't really affect the ions, although a strong enough magnet will affect ions, but it'd take more energy, a super strong magnet, to even do that. a lot more energy than this TV can produce from its power supply. Ions are quite heavy, quite massive. So they're just atoms. That's all an ion is. And it's either an atom that's got one or more too many electrons, which will be a positive or a negative ion, or an ion that's stripped of electrons, which is a positive ion. Most of the ions in a TV, or most of the ions you're going to find in here has got some electron strips, so they're positive ions, but they are an atom. So that means it's got the massive nucleus and a few other electrons with it. So the magnet really is only strong enough to straighten out, when it's in the right position, the electrons so that they'll shoot out, straight out into the screen, whereas the ions will continue on their path to not hit the screen. Now, at some point in time, it was determined if you take aluminum and put into the front of the screen, right up near the front of the picture tube, just right between the phosphorus screen and the gun, if you put a thin layer of aluminum there, that you could literally stop the ions. Now the reason for that is because of a thing called density. And everybody knows that aluminum is lightweight. And compared to, say, copper, lead, silver, gold, iron, steel, whatever, it is much lighter. Now part of its weight reduction, or being a little lighter, is the fact that what they call the atomic number of aluminum, which is the weight or the mass of the nucleus, and is the mass of the atom for all practical purposes, is a little lower than those other atoms that I mentioned. But the biggest contributor to this is the fact that the aluminum if you take a certain size, cubic volume of a certain size, I don't care what size, but it's got X size sides, a cube. You take that volume and you count the number of aluminum atoms in it, it's a lot less than the more dense materials such as lead, gold, copper, and those materials. They have far more atoms in that volume. And that's what density is the number of atoms in a material in a certain metric volume, or certain size of volume. So, being that aluminum has very few electrons per cubic something, whatever size, it's going to be a very small size, atoms are quite small, then it is actually fairly open. To make a solid, basically, the atoms kind of build up a latex crystalline structure where you'll have an atom here, and like maybe here, and then one here, and they'll build up these structures where there's atoms at certain points, and they stay there. Now, to keep from getting any comments, they do vibrate, but they don't move any more than just a little vibration, and that makes it solid. But in between those atoms, there's empty space. And if you got a very low density material, there's quite a bit of space. That space allows the electrons from the electron gun to easily transverse through and go on and excite the phosphorus. Whereas the ions, which are atoms themselves, are much too massive to make it through. So they just get bounced off. They can't go through. And a nice analogy of this would be if I took some sort of net, maybe made up of wire or something solid, but hard, but a net that had say openings in it, or was made up with the openings in it of about something about this size, about the width of my hand, on all the way around, little squares like that, all through the net. And I got this net setting up there, and I start throwing marbles at it. Well, I'm going to be the probability is going to be pretty good that I can throw the marbles right through that net without any problems. It's not going to hit anything. In fact, I'll have to be really accurate to hit any of those thin wires, even at the cross points. So if I threw 100 marbles at it, the vast majority, and could very well likely be all 100, will make it through the net. But now I grab me a basketball and try throwing through there. It's just going to bounce off the net. It's not going to go through. Well, that's how the aluminum actually works. Now it's real thin, because the thicker it is, then that means that crystalline structure starts overlapping itself, and then those openings get smaller and smaller. So you make it really thin, and the electrons just go right through without really any interaction whatsoever with the aluminum, and they go ahead and make it to the phosphorus. But the ions, which would be like the basketballs, they just bounce off. They can't make it through. Now the other advantage of aluminized screen, picture tube, is that aluminum is put on, if it's put on in a fine enough coat and flat enough, it becomes quite reflective. Now in a regular picture tube like this one, if we kind of look at it from the standpoint of the screen, we got the screen here. The phosphorus is just on the other side of that glass. Now when the electrons come through and they excite that phosphorus, light shoots out. But as much light is going out forward, there is light going back inside. This light going in here does me no good. It doesn't help, it doesn't do anything for me. But if I could put a reflective surface there, that's going to bounce that light back out to the front. So in theory, I get twice the amount of light. It doesn't quite work that way, but it does increase the brightness and the contrast of the picture tube. So you get two things from a aluminized screen. You get the protection of the phosphorus from the ions. You don't have to deal with a magnet here up on the neck. No magnet here, no bent gun, no none of that. But you also get the reflectivity, reflecting the light out that normally would go back inside the picture tube. You reflect it out, you get a brighter image and a better contrast to that image. So you're getting two things out of this. Now I said something, and if you caught it, I said the electrons go up and excite the phosphorus. The electrons themselves is not, under normal circumstances with the normal voltages and the normal amount of contact time, in other words, as long as the picture tube's operating correctly and it's sweeping across, will not damage the phosphorus. Because what they actually do under normal operating conditions, what they do is when they get that phosphorus atom, they hit electron that's on that atom. Now going from a basic Bohr model, we can say the electrons are in orbit around the atom. There's several of them, so there's several orbits, and they hit one of those electrons, they distill their energy to that electron that they had from being accelerated forward. They develop a certain momentum and energy. They give that energy to that electron that they smack into, which causes it to jump to the next orbit, further away from the nucleus. It's a higher energy level. It doesn't want to be there. It wants to be at the lowest energy level it can possibly be. All the electrons and all the orbits on that phosphor atom are where they're at because it's the lowest energy level they can be at. So that's where they want to be. So just right after it has been moved to the higher orbit, it jumps back. When it jumps back, it has to get rid of that energy. The way it does it is it produces a photon of light, which is a particle of light. And that shoots out. And that's what you see. No damage has happened to the atom whatsoever. Now, if I concentrate too many electrons there, say like I lost my vertical, or worst case scenario, I'll lose vertical and horizontal, and when I just got a dot, either case, if I concentrate them there too long, then that bombardment may end up starting to strip them electrons completely away, giving them so much energy that they completely leave the phosphorus atom, which basically the atom doesn't work anymore, doesn't do its job, it doesn't produce light anymore, it becomes dull. So, or if I put too much second anode voltage on, in other words, a high voltage going here to the lead, if it's too high, something wrong with the circuitry and it's too much voltage, then the acceleration is too great, the energy is too much, and you can also do the same thing. So, but under normal circumstances, no harm is done to the phosphorus. So anyway, that deals with that. Now let's talk about focus. Now this picture tube here uses electromagnetic focus. It's just a big coil that fits around here, around the neck, and we energize it from the power supply with DC. It produces a magnetic field. It's controllable with a rheostat that's across it and parallel with it, and you can adjust how much voltage is actually going on that coil, and that will increase or decrease the magnetic field, which will increase or decrease how much focusing it does. There's another type called electrostatic focus. Now early sets with electrostatic focus had a lot of picture tubes like the 7JP4, which was electrostatic deflection and electrostatic focus. A lot of those had variable focus, just like the magnetic. You could adjust it, you had a control. It didn't take them too long to realize that any of the focus controls, once they're set, whether it's magnetic or electrostatic, and as long as the set's working in its normal operating mode, you know, the voltages are where they're supposed to be, everything's working right, then once focus is set, it don't have to be set anymore. And TV manufacturers, being like any other manufacturer, if I can get rid of components that I can put in, that saves me money. You know, controls cost money, wire costs money, all this costs money. So they started looking for a way, since they knew that for all practical purposes, for the general life of the TV, that once focus is set, it don't have to be reset all the time. It's not like, you know, fine tuning or anything like that. And brightness and contrast and some of those controls, it's not a control that gets used a lot. So they wanted to come up with a way, and they worked with the manufacturers of picture tubes to work out a way that you could have a focus that is just set at the factory. It is set. No controls. We just give it a certain voltage and we're good to go. And as long as that voltage and the other voltages in the set stay where they're supposed to be within their operating ranges, it'll stay in focus. Now if something starts, you know, a component starts failing, another tube, one of the tubes start failing or anything like that, starts throwing off some of the voltages and stuff, yeah. But that's an area where it goes in and gets repaired, and you don't have to adjust the focus again. You didn't have to. You just get the voltages back where they're supposed to be, and everything's good. So we're going to show how that works. We're going to be talking about electrostatic focus in a little bit newer picture tube that is fixed. Because what you will find, some of these will have maybe two fixed voltages, like 0 and some positive voltage that can be quite high. It can be like 0 and 400 volts or something of that nature. Some of them may have 3, and they just have a wire like that you plug or move around. Some have actually a deal that, because the focus pin's usually around like pin number 6, and they'll have a little piece of metal that actually hooks on there. You can either take it off or put it on. When you put it on, you got a certain set voltage. You take it off, it's at 0. So let's talk about how that works. So I'm going to slowly kind of zoom you around here. We'll look at the whiteboard, and we're going to look at some information. And see if I'm zoomed all the way out. Let me I'll probably have to raise you up a little bit because we're not going to get a good shot of this whiteboard. And we'll move you a little closer in. So bear with me. Kind of rough ride there. Alright. Okay, I think we can catch most of it. Alright. Now, I had a couple picture tubes, both of them bad. One, the gun's pretty well used up. It would register barely into the red. Even after trying to rejuvenate it, it didn't help it. And the other one had a dead filament. The one, by accident, the neck got broke. The other one, I went ahead and pinched her off and let the air out, let the vacuum out, let air into it, and then broke the neck off. But here's a typical gun of a little bit newer electrostatic focus, straight gun. And I've got the other gun, which I kind of tore some of the parts apart so we can talk about. This is the control grid right here. And see if I can get that up a little closer. Inside this is the cathode and, of course, the heater. This is the first anode. And then this apparatus here is made up of this piece, and this piece. Each one of them is called a grid. But this is grid number 4. This one here, if I rotate it around, hooks to this lead and goes over to this pin here on the back of the tube. And we'll have a certain voltage or even 0 volts supplied to it. These two parts are connected together. This grid and this grid. Connected through this. Then they're connected to these parts here that flare out. And right here on the end is the getter, which is connected to it. Inside the picture tube, there's a coating that is conductive. Remember, a picture tube has a coating on the inside. That's for what they call the second anode, the high voltage, to accelerate the gun or accelerate the electrons so that they'll hit the phosphor screen. On the outside, you'll have a coating on most picture tubes, the aquadag, as it's called, and that is generally grounded or connected to chassis ground or B minus. and between those two you got glass, so you got a capacitor, and they usually newer sets, a lot of them use that as the filter cap for the high voltage. Well, this contacts a second anode coating inside. So all this part right through here, these two pieces, these two grids and this, as well as the getter and everything, is at the second anode potential. This part right here, which is just a tube, you can see down through there, maybe, just a little tube that's hooked to this, is connected to a lot less voltage, or even possibly 0 volts. So now we're going to see how that works. Now, one thing you need to understand, there are two focus points that happens in a picture tube. One, bring the gun back up here, happens right up front, right at the cathode in the first grid. That control grid, grid number 1, is always going to be basically negative. So it actually forces that whole bunch of electrons coming off the end of the cathode to squeeze down to a point which will actually go through. And if I can show it to you, and I don't know if I'm going to have enough light, because I don't think I can shine light through it and then not affect the camera. That may be too much light. But there's a very thin hole right at the very center, and I don't know if you'll be able to see that. I don't know if I can. There, you might be able to see a little bit of it coming through. Okay. That is the very thin hole that the electrons are focused down to a real thin point that comes through there. The electron gun sits inside there, and this is a cathode, or I mean the cathode sits in there, and this is a cathode, and it's just a cup, but pretty much all the oxide coating is concentrated right at the end, so everything shoots out. You can kind of see it looking dark right there. Okay, that's where the electrons are produced. And of course, inside that cup is where the filament goes, or the heater, and that sets inside the grid. Now there's a little spacer that goes in there too. Now on the other side of that grid, right after it, right up close to it, sitting real close to this, is like that, is the first anode. And this will have a certain amount of positive voltage depending on the tube, generally 300 or 400 volts or something of that nature, and it's got a very small fine hole that maybe you can see that the electrons go through. Now once they're at a point, once you ever bring something down to a point, it gets to that point, comes in, and then it wants to start coning back out. So it's kind of makes up something like this. They come in this way, come to that point, and then they start spreading back out again. Well, it starts that fairly soon, so if we didn't do anything else with any type of focus, by the time it got to the screen, they'd be spread out more than the width, the size of the screen, and you wouldn't get virtually hardly anything showing there. You might get a little bit of glow in a real dark room, but that's it. So we need to focus it down. Now with the magnetic type, you have a magnetic field produced by a coil on the outside, and that's what squeezes them back down. So they'll start going down, and it's all designed so that it squeezes them down to a point where they come to a point right at the screen. But electrostatic, what we have, and I just drew up the parts right here. So it's kind of setting pretty much like this. This part is right here. This part is this right here. And this part is this part right here. Now, I pulled up information on this, or a very similar picture tube of this. I couldn't find exactly this, but I found something real close to it. It uses the same gun, so it's basically the same. The anode voltage on it runs around 16,000 volts. So these two parts are at 16,000 volts. So this and this is a positive 16,000 volts. The standard that they're looking for is somewhere around 400 volts to the focus ring, this tube. But it can be zero. It can be anywhere from 0 to 400 volts. That's this part right here, which is right here. That's 400 volts, positive. The thing is, when I look at 1600 versus 400, this 400, there's a big difference. And since they're not actually connected together in any way, shape, or form through resistors or whatever, then this voltage and this voltage being different, this one is 1600 subtract 400, which is 1200 volts. It's 1200 volts more positive than this part. Or this is 400 volts negative respect to this. So we start out here and we've had a pinpoint focus, but now it's starting to spread out. And it comes in to the first part here. It's being accelerated. Remember, this is at 1600 volts. So it's really pushing it through here. It's pulling those electrons. They get inside here. Now, since there's a big difference in voltage between these two, it develops electrostatic field. And my drawing's terrible. These would be really curved in here. But we get electrostatic field that goes across here. It'll actually go from here to here and from here to here. And what that does, that is actually negative. It is pulling what is apparently negative respect to this. It's making this look negative, so this electrostatic field actually becomes negative, or appears to be negative to these electrons. So that curves, which will really come real close to these, the electron beam, will start pushing them in and start breaking them in and pushing them in, so that they start shooting out at an angle that is directed towards the screen somewhere out here. And if everything's done right and the focus is correct, the geometry's been done correctly and everything, this will come to a point right at the phosphors. So you have a fine point there and a fine focus. And basically all the focus really is think of it like a lead pencil, old-fashioned lead pencil, wood with lead center like you had in school. Not mechanical, but an old-fashioned lead pencil you had to sharpen. Well, after using it for a while, you haven't sharpened it for a while and you've been using it writing numbers, drawing, everything else, the lead gets really rounded off and it starts producing some really, really wide lines. So maybe you don't like that. Maybe you want a little finer. So you take it to the pencil sharpener and you sharpen it up until you get a real fine point on there. Now it's going to produce really crisp, fine lines that are really crisp and neat looking. That's what we're doing with the focus. When we focus that down to a point onto the screen And then the magnetic fields that are produced by the yoke starts tracing out on that screen. It's going to be real nice, fine, high definition relative lines, really in focus, so that the picture, the video that it makes, whatever's being displayed, will have crisp lines in it. Will be nice and crisp, good contrast on them. Now, why have different voltages? You know, and why not variable and things like that? Why a lot of times a lot of these will either be like 0 volts or 400 volts in this case? Why not something else? It has to do not only just with this focusing system and the anode, but it has to do with all the other control elements in the tube. It has to do with how it's modulated, the modulated strength signal, in other words the video signal. It has to do with the voltage on the control grid and everything else. And I figured the easiest way is if I could find some decent documentation on a picture tube that's got this style focus, it would answer your questions a little easier. So we're going to come down so you can read something, and I'll read it to you so you don't have to basically read. Hopefully we can get in on that. Okay, what it says here, it's a notation on grid number 4 voltage, and they said they do have typical operating conditions showing 200 volts, which may work just fine for this tube. But they do say here, the grid number 4 voltage, which is this focus voltage, that outer shell, remember, that's grid number 4, right here. Grid number 4 voltage required for optimum focus of any individual tube will have a value anywhere between 0 and 400 volts, with the combined grid number 1 voltage and video signal voltage adjusted to give an anode current of 200 microamperes on a 13.5 inch by 18 inch pattern from RCA 2F21 monoscope or equivalent. Now they're actually putting a pattern on there, but what they're looking for is this 200 microamps with the combined voltages of grid number 1 and video signal, and that's going to determine where this focus voltage is optimal at. But it can actually be anywhere between 0 and 400, and it can be or just 1 or 2 of them. But it's going to be one or the other of any two voltages. And sometimes it can be both, but for the most part you can pick 0 and you can pick something that is around close to 400 or even 200, as they state in typical operating conditions here, depending on when you do the testing of what you're getting for your grid number 1 voltage, what you apply to it, and how strong that video signal voltage is going to be under normal operation conditions. And this all has to do with not just the geometry. What this is affecting is this front focus area right up here, where this happens at exactly, because that affects this geometry. It affects how wide this is going to get, or how narrow it's going to be, requiring how much electrostatic is going to be needed to pull it in, pull it out. But this is the information that the TV engineer will have, and when they first do their prototyping and building the set, they will determine from this what they need. And once they set it, it's preset, it's done. Now they may give you the opportunity to jump between, say, 200 volts in their normal operating conditions and 0. They may even have 0 and 100 and 200. Or they may have 0, 200, and 400. Just in case some of these conditions change. Maybe some of the voltages and the video signal voltages and the grid number 1 voltages shift just a little bit due to age of components and stuff. It's not out of tolerance, but it's moved a little bit, and it's enough that you can switch to one of the other voltages easily, and it'll work just fine. You'll bring it back into focus. But the whole idea of this is we've got a preset geometry that's going on here. The only variables to that geometry is the other voltages that's in the set. That will determine what this preset voltage needs to be. And all that will be determined by the TV set itself, its circuitry, because we're looking at grid number 1 voltage and video signal voltage to take care of that. And as well as, to a certain extent, you can actually say what is happening with that anode voltage as well. It can be 16,000 or even 18,000 volts on this particular set, but this is 24 inch. This one's out of, or the one I'm actually working with is 23 inch. And its schematic says it has 16,000. And actually, I believe it was operating at 400 volts on its focus. It was either 0 or 400. Now, remember one thing about this for the most part. On the ones that you can actually move a wire, 0 volts will probably be ground in most cases. That's a relative term. So it's relative to a lot of other voltages in there. That's in the set, but that's actually B minus. That's part of all the circuitry. Okay, ground is B minus. So even though it's 0 volts, it still has a relative thing. What it does is increase the strength of this electrostatic field, because now I got even more difference between this point and this point, a greater difference. Now on sets where there's just a piece of metal right on the tube base that you can either take it off or leave it on. If you leave it on, it may be, 2, 3, 400 volts there. If you take it off, there's nothing there. How does that work? Because that would be effectively, I am opening this circuit. There's nothing there. So how does that work? Well, you got to realize, one thing you got to remember, this is electrostatic. It's static electricity. Static. Static meaning no motion. So it's stationary. So I'll throw something at you. Winter day, cold winter day, you're in your house and you're walking across your floor, and maybe you want to look outside, open the door and look outside. You got a wood door or fiberglass door or something of that nature, metal handle on it. And the air's really dry because it's a winter day, the heat's been on, and you walk across that carpet and all the conditions are just right, and you get there to that door handle and you grab that door handle and it bites you. You get a shock. Well, it's static electricity. But the door handle's out free in space. How can it have any charge? How can it have anything on it? It's out there and free in space. It's hooked to a wooden door, which is insulated, or a fiberglass door, which is insulated. So what's going on here? Well, what happens is, as you're moving across that floor, you're building up an abundance of electrons on your body. Now, static electricity is a surface effect only. So it stays on the surface. The charge will stay on the surface. If it goes underneath the skin in there, or say a piece of wire, and it goes inside the wire, it there's no more charge anymore. It neutralizes itself. Only the surface will have a charge. As you approach that door handle, getting close to it, you get where that negative field that has developed around your hand due to the abundance of electrons starts drawing a positive charge on that door handle. And simply what it's doing is it's the electrons, that negative field is causing the electrons that's in the atom, on the atoms on that door handle, to move away, because like charges repel each other. So it's repelling those electrons, making the handle more positive, right where you're going to touch it. And when you get close enough that an arc can develop, then you get shocked, and then it neutralizes itself. But the fact that as you get close, it actually does this, is how this thing works. If I have nothing connected here, then what happens is this positive voltage will have a positive field around it, positive charged field, and it draws electrons in this metal to the surface. All around this thing gets drawn to that surface because they want to go there. Any positive charge here wants to go away, so the negative charge comes and replaces it basically by the movement of electrons, and this starts becoming very negative charged. When you have a positive charge here and a negative charge here, you develop an electrostatic field that transverse in static electricity from negative to positive. So it transverses this way. Again, we have the field. Again, we have focus. So that's how those work. So whether they're connected and actually connect to ground, or we just take the clip off and it's just floating in space, either way, it's going to basically become negative due to the influence of this positive charge here. In either case, we're going to build up this negative field that's going to push those electrons in, and it's going to push them just right, just the right amount, so that when they get to that screen, they come to a point, and we have it in focus. So this has been really a long video. I hope I explained this well enough for you to understand. I didn't want to make this too complex or too complicated. I didn't want to go deep in theory about how everything works. I was more interested so you just get a feel of both about the bent gun and all that stuff, as well as the ions, the ion trap magnet, as well as the luminized screen and how it works and its benefits, as well as the focus. Now the magnetic focus does the same thing except with a magnetic field. It's doing the same thing as this. But I thought this is mostly important because it's somewhat, I think, easy for a lot of people to understand when you have adjustable focus. How, well, if it's magnetic, I increase the magnetic field, it squeezes them down more. And if I decrease it, they spread out more, because the field increases or decreases in strength. Or if it's an electrostatic focus that's adjustable. But how does the fixed one work? And that's how it works. It's making use of preset geometries between all the elements and a certain set of voltages that are existing in the tube. And all this comes together to create the geometry that allows us at a certain preset voltage to be able to focus that down to a pinpoint. Now all those geometries and everything will vary from tube to tube a little bit. Different types of tubes. There are different geometries as far as the distances from the neck of the tube to the screen, and deflection angles and the whole 9 yards. All changes in geometry will make do that some of these elements have to be adjusted, and that geometry and maybe some of the voltages that are required be adjusted as well. But that gets into actual designing of picture tubes, and that's beyond the scope of these videos. These videos are designed just to kind of understand the basics of how they work. So, I think that's about all I've got on this. If there's any questions or in the comments or anything, I can come back to this and work it up, and we can go over it again and stuff. Now, the biggest thing, before anyone asks, basically, this just is a pattern. It's a pattern generator, basically, that is that's being produced. They're just running through a monoscope, using a monoscope because it's a black and white picture tube. But they're using a 13.5 inch by 18 inch pattern. Okay, that's what they're going to send a signal to that picture tube on the video signal. So that's all that means right there. And what that does is that pattern will create a certain amount of current draw, along with all the other voltages and everything, that will end up with a 200 microamp current draw. So anyway, I guess that's, like I said, that's about all I've got on this. And if you have any questions, I'll come back on this, unless I can answer them pretty quickly and easily in the comments. So I want to thank you for your comments and your kind words, and thanks for watching and everything. And if you like this video or the videos like this, give it a big thumbs up. If you're not subscribed, please subscribe. There'll be a lot more videos like this, and on a lot of other stuff dealing with tube electronics. And we kind of get into a little bit of everything dealing with electronics and theory and stuff. So again, I thank you, and everybody have a good day, and I'll see you guys on the next video.